Hello, in this video I want to explain how to generate the AWGN noise with the correct power spectral density on MATLAB. So first of all, on communication system simulations, it is usual to have the information from the noise, the target noise floor, that is the target noise power spectral density, not the actual noise power. So let's define first a noise floor, a target noise floor. Okay, so let's say we want a noise floor of minus 135 in dBm per hertz, which is a reasonable number. Okay, so after this, we want to convert it to dB per hertz. So noise floor in dB per hertz is equal to noise floor in dBm per hertz minus 30, okay? And then to convert into the units of watts per hertz, we want a noise floor in watts per hertz is equal to the noise floor, 10 to the power noise floor divided by 10. Okay, so this is the noise floor in watts per hertz. Now, the next step is to calculate the total average noise power. And to accomplish this, let's assume for this a baseband system. So let's assume a baseband system, and the horizontal axis we have the analog frequency, and the vertical axis we have the noise PSD, which is flat since it's a AWGN channel. We are assuming an AWGN channel. So let's assume the bandwidth is B here. So here's minus B. Okay. So the total power is equal to this area here. So the total power of the noise is equal to 2 times the bandwidth, and remember we are assuming a baseband system, times this PSD here. Let's say this is Sn of the analog frequency f, Sn of f. Okay, so on MATLAB, let's first define a bandwidth for the simulation. Let's say 100 megahertz. So this is in units of hertz, and we have 100 megahertz here. Okay. Now the average total power is noise power is equal to 2 times the bandwidth times the noise floor, or the actual PSD, in watts per hertz. Okay. So now we have the noise power. The next thing we need to consider is that the total power of a random process is equal to its mean square value. So it is equal to the expected value of the absolute square of the samples of the sequence. And this, whenever the sequence has zero mean, so mean is equal to 0, that is, the expected value of the sequence is equal to 0, then the mean squared value is equal to the variance of the sequence. So on MATLAB, we already have the total power of the sequence. And remember, it is 2 times the bandwidth times the PSD. So now we just need to generate a sequence with the variance equal to this total power. Let's do that now. Well, let's define first the number of samples we want in this sequence. And let's say it's 4096 samples. Okay. So MATLAB has a function called randn. This function generates a sequence with zero mean and an unitary standard deviation. That is, the variance is equal to 1. Okay, so let's generate the sequence and verify it. Okay, so let's evaluate that. add clear all here. Okay, let's evaluate this, and then let's say noise is equal to rand n with n samples, capital N samples. Okay. So let's verify the mean of the noise. It is, well, the number of samples here is too short for the expected value to achieve the correct value. So let's increase it. Let's say we want n samples with this number of samples. Let's say it's 100 samples. And now multiply here. Okay. Okay, so now let's verify the mean of the noise. It is it is closer to 0, and let's see what the variance is. Variance of noise. It is very close to 1. So we know MATLAB is generated sequence which in reality has 0 mean and unitary variance. To modify this, we need to multiply it by the square root of the variance we want. Okay, so we want to generate a sequence with a specific variance, and this specific variance is actually the total noise power. Okay, so let's evaluate the whole script now. Okay, and now let's see the total noise power. And let's see what the variance of noise is. It is the same, so it's correct. Okay, so far we know we are generating the sequence with the correct variance, that is, it is with the correct total power. So we just need to verify now that the power spectral density is the PSD we want, which is the one that we defined in the beginning, minus 135 dBn per hertz. Okay, first I want to estimate the PSD of the noise we are generating using the simplest form of PSD estimator for discrete sequence. Well, the PSD estimator is called the periodogram, and there are several more complex and more accurate techniques for estimating the PSD. So we want to use the simplest, which is the FFT. Remember, in this simulation think of it as several symbols in series. You see, each of those symbols has n samples, capital N samples. So we are sending 100 symbols. Remember, 100 symbols we define this way, and each of those symbols has 4096 samples. So what we are going to do is to take the FFT, x of k, of each of those symbols, and then take the absolute square of this FFT, and we want to average this. So we are going to take the expected value of this in order to have a good estimation of absolute square of the FFT, the absolute square of the FFT. So after we do this, the PSD estimator is defined as, let's use Sk is equal to the expected value of the absolute square of the FFT divided by n. And the total power is going to be equal from k equals 0 to k equals n minus 1, and in this case n, capital N, is the size of the FFT. So the total power is equal to summation from k equals 0 to capital N minus 1 of the PSD estimator times the delta capital F. And this is the distance between two digital frequency points from the FFT. And remember, the digital frequency goes from 0 to 1. The FFT divides this interval into n spaces. So delta capital F is equal to 1 over n. Okay. So the total power is equal to summation from k equals 0 to n capital N minus 1 of x k times 1 over n. Okay, and this estimator gives the PSD in units of, let's say, volt squared, or let's use another representation. Let's say it is watts per subcarrier of the FFT, not watts per analog frequency, per hertz. So in order to have the PSD in watts per hertz, you still need to convert it by dividing Sk by the sampling frequency Fs. So this is the final estimator we want. We want to have this PSD estimator, the average, just for completeness, the expected value of the absolute of the FFT squared divided by n times the sampling frequency. Okay, so let's do that now on MATLAB. First of all, I want to split the noise symbols. Remember, we are sending a string of noise symbols, each with a capital N samples. So we want to use noise split is equal to, we use a function called reshape, which gets the string and splits it on the size we define. So in this case, the string we are reshaping is noise, and we want it to be split in a matrix with n rows, capital N rows, and n symbols columns. Okay. Now we want to take the FFT of this FFT. So let's say noise with capital N in the beginning, noise splitted, equals FFT of this. The N capital N point FFT. Now the simplest periodogram is Sk. Remember, we want the expected value, the mean, the expected value of the absolute squared of what? The absolute squared of the FFT. So let's pass this here, okay? And we take this absolute squared, the mean of the absolute squared of the FFT, and divide it by n. And this results in units of watts per subcarrier of the FFT, per FFT subcarrier. Now, to convert it into the units we want, that is to convert to watts per hertz, then let's say Sk watts hertz, we still need to divide it by the sampling frequency. Sampling frequency Fs. Since we didn't define the sampling frequency before, let's define it Now here, sampling frequency fs is equal to 2 times the maximum frequency in the spectrum, assuming we are sampling in the Nyquist rate. So sampling frequency, okay. So now we have the PSD estimator in watts per hertz. Let's comment here, watts per hertz. Finally, we can convert it to dBm per hertz. So let's copy from here, convert to dB per hertz first. Sk dB per hertz is equal to 10 times log 10 of Sk in watts per hertz. And then let's convert it into dBm per hertz finally. So it's simply Sk dBm per hertz is equal to the value in dB per hertz plus 30. Finally, we want to plot the results over an analog horizontal axis. So we need to define the tone spacing, the FFT tone spacing, which we know from the theory that the FFT tone spacing is the sampling frequency divided by the FFT size, which is capital N in this case. So let's generate the plot and first define the horizontal axis, which is from 0 to capital N minus 1 times the tone spacing, which is delta F, and then the vertical axis, which is the PSD in dBm per hertz. And there is a detail here that we need to say MATLAB to average the FFT of the noise over the columns. So we say mean and we use a comma and then specify the dimension 2, which means average over columns. So after this we can run the script and then we see the results are well approximate on the noise floor we specified in the beginning. Remember, it was minus 135 dBm per hertz. So just for the sake of clarity, let's label the plot. Let's say frequency, analog frequency, and let's divide it by 10 to the power 6 to have it in megahertz. And let's label the vertical axis as the noise PSD. Okay, right again.